let's take a look at question number 1. So it says a block at the end of a spring is pulled to position x equals a and released. Through what total distance does it travel in one full cycle of motion? Do you guys want to vote? Do you want me to?
Yeah.
You want to vote?
Yeah, sure.
All right.
Okay.
A over 2. A. 2A. 3A or 4A? Okay, so I see hands up for both 2A and 4A. Defend. You got this. She's like, I got this.
Okay.
All right, we're going to go here and then I'll come back there if we need, okay? Is that okay?
Okay. So A is the displacement from equilibrium. Yes.
Mm-hmm.
So, and direction doesn't take into account direction. So it's like just how far you've traveled, like, and not like the most direct. Yeah. So if that's A, then you're going to equilibrium, and then you're going to go negative A because it doesn't take in account direction. It's going to be at that point it's going to be 2A, but it's only half an oscillation. So then you have to go back to equilibrium, which is another A, so that's 3A, and you have to go back to your original spot, which is 4A.
Does that make sense? For my friends that said, so you're arguing for 4A, is that right? So she's arguing for 4A. My friends that said 2A, do you agree with her? Is there something that we missed?
Assuming it's an ideal spring. Yeah.
True. Point taken. Yes. We always assume it's an ideal spring. Yeah. How are we doing? Are we okay?
But wouldn't oscillation just be from A to B? Wouldn't it just be 2? Wouldn't that be 2 oscillations to go back to B?
Is this where you're saying B is?
Yeah.
Okay.
Because if on the graph, wouldn't A to B and then B back to A be the exact same as each other? So then wouldn't that be... Why
A
not?
to B would be left, and then B to A would be. That's one thing.
So we have to figure out what an entire cycle is, right?
It's from one point and then back
To the original.
Back to the same point. Does that kind of make sense?
Like
So if you're talking about like a
sine chart. Like a sine chart, it starts at 0, and then one period ends at 0, or like y equals 0. So
you're saying like from here
yeah,
to
there
here.
is one.
That's A to A,
Cycle.
the one towards B.
Does that kind of make sense? Yeah, we would if we were going to do displacements, we need to shift this over and start it from like here, right? Does that? But yes, yeah.
Cosine.
Does that help? Okay. So we okay with that? With D being the answer for that one? Yeah. Okay. Are you ready to discuss number 2 as well?
Yeah.
All right.
Yes.
Little uncertain, but we're going to go for it. For a simple harmonic oscillator, which of the following pairs of vector quantities can't both be in the same direction? So to be clear, we're saying cannot, are not able to, will never be in the same direction. The position vector is the displacement from equilibrium. Position, velocity, acceleration, position, acceleration. What are y'all voting for? What do you say? C? C sounds good? Okay, so then what's my next question going to be?
Why?
You got it. It's like you've known me for a little while. So answer the question, will you please? Spencer, go for it.
The equilibrium point, as shown in the picture above, is like, if that is 0, then when you pull it to x equals A
Okay.
and you let go,
Okay.
the acceleration will be negative.
So the acceleration is going this way?
Yes. So
Okay.
Since that's the negative displacement, that'll be in the negative. That direction is negative. And then the second it hits equilibrium, it'll switch to a positive.
So when it's over here, it's going to feel a acceleration like this?
Yep.
Is that what you're saying?
Yep. And then
Okay.
the position on the right side is positive while the acceleration is negative. And then once it crosses 0, it becomes negative. So they're always opposite.
How are we doing? Does that make sense? Can anybody tell me? I mean, I agree with you. I want to see if we can distill it down into a simpler description, though. Is that okay? Jacob, you were about to say?
Well, the box stops, so the acceleration has to be in the opposite direction from where it's like traveling, or like where it's traveling like from A to equilibrium, or from equilibrium to A, so it's moving right, but eventually it stops when it hits A, so the acceleration has to be in the opposite direction for it to stop.
Okay.
And then once it starts going the other way, so it's still on the positives, the position of the positive side, but the acceleration is still pulling it to the left. And then it's switching across equilibrium.
I think what he's saying is that in order for the thing to change direction, there has to be a point where it changes acceleration, because otherwise it'll just keep going.
So, okay, I have to ask a question because I'm not sure I'm understanding what you're saying. I think that I was with you and then I lost something there. So as the box is traveling this way, this green arrow, which way is the acceleration going? Positive or negative? Negative. And then it turns around and it starts traveling this direction. Which way is the acceleration?
Or ways.
It's negative, but the position's still positive.
Okay. Do you see where the hiccup was coming? So you have to make sure, and this is one of those things, guys, that when you're answering those free response questions, you have to be careful about the words you're using, because the words that you're using have to match what you actually mean. Thanks. Okay? So again, let's see if we can find something a little bit more succinct. You're not wrong. I agree with you as long as you're careful and got to be careful not to say too much, because sometimes you dig yourself into a hole.
Wait, so the way I thought about it was that position and velocity are directly related because velocity is meters per second
Okay?
and it's delta x over t, and t stays the same if you're thinking about all of them. It's like just a non-existent variable. Well, not non-existent.
Okay.
That doesn't make any sense. But so position, if the position is positive, then velocity also has to be positive.
Does it?
Because it's x over t, right?
If position is positive, so that's anywhere over here, right? Does the velocity have to be positive?
Like after it hits A, it's traveling to the left, but the position's still positive. So the velocity is negative.
So you can have a positive velocity and a positive displacement. You can have a negative velocity and a positive displacement. You can have a negative velocity and a negative displacement. You can have a negative velocity, or a positive velocity and a negative displacement. So these can be the same or different.
Like, yeah, they can be, but then B can also be the same or different because you can have a negative velocity and a positive acceleration.
That's true. So that one can't be that one. So process
elimination.
elimination. Is there physics that can show us the right answer? The answer is yes. The answer is it's a very simple equation. You probably have it written on your gold sheet. Maybe you don't. I don't know if you did or not. If an object is accelerating, what does that mean is acting on it, friends? Yeah, what kind of force? Oh, what is the spring force, you guys? Oh, and that's the only force that's acting, which means that it's got to be accelerating, yeah? F equals... Oh, are you with me? And I don't mean this in a duh sort of way. I mean in a we have to make sure that we've got physics to back up whatever we're trying to argue. If X is positive, this side right over here has to be what?
Negative.
Negative. And if this is negative, what do we know about the A?
It's negative.
It's negative because M can't be negative. If X is negative, this whole thing's got to be positive, which means the acceleration has to be positive. Yeah. So really, it's just Hooke's law. Hooke's law is the thing that proves to us that that's got to be true. Okay? Remember, Hooke's law says that the force is always in the opposite direction from the displacement. It's like one of the fundamental tenets of it. You know it. Okay? If you don't have that written down, you may want to write it down again. Hooke's law is like one of those things you can write down all day, every day. It just keeps being true. It's great. Do you need a moment to discuss number 3?
No.
I'll give you 30 seconds to make sure you agree with your partners because I know that not everybody's feeling it. Go ahead. 30 seconds. It's going to be a fast one.
Well, when you let them go. You're pulling it further.
All right, my physicist friends, let's do it. If the amplitude of a system moving in simple harmonic motion is doubled. Which of the following quantities, keyword here, does not change? You ready to vote? All right. Raise your hand if you think it's total energy. Raise your hand if you think it's maximum speed. How about maximum acceleration? How about period? All right, period. All right, so y'all are voting for period. So now the next question I'm going to ask is?
Why?
Indeed. Why?
Well, I know that it's not A because
How do you know it's not A?
when you pull it, the amplitude is like the displacement. So you pull it further,
Okay,
you're giving it more spring potential energy.
because spring potential energy is,
Squared.
okay, so if we increase X, we're increasing that. So how does that have to do with total energy? I think you kind of said it, but I wasn't 100% with you.
Energy, you pull it
When it
further,
does,
you have a
it's
higher
energy.
spring potential energy. So,
And does it have any kinetic when it's pulled out all the way?
oh,
No. Yeah. So all of the energy when it's way out at the at A is just spring potential. So that's going to go up. Okay. So I'm convinced it is not A. We have not gotten there yet. I'm not going to let you talk the whole way. Share the fun. Go.
So speed has to do with kinetic. So it's like the same kind of thing. So kinetic equals 1/2 mv squared. So it's like if your US is increasing, then at equilibrium you have to have a K equal to US because there is no spring potential. So it's like, so that K is gonna change as well.
What do you guys think? Does that seem reasonable? So if X gets really, really big, US gets really big. If US gets really big, V gets really big. That's what you're saying? Okay. That's convincing. 2 down. Jacob?
So acceleration, so mass times acceleration equals the force of the spring, which is equal to negative kx. So if the x is increasing, the acceleration will also increase.
Okay. So I got on you a little bit on this other one about, like, yes, you can use process of elimination, but I want you to use physics as well. This one we're using process of elimination because we don't really know anything about period. We're going to get there today or tomorrow, so we're going to hold on to this. But I would agree that the answer is period because we know that it's not the other three for sure. Sometimes you have to do that, right? ACT. Sometimes you have to do that on an AP test. Sometimes if you don't know, you get rid of the things you don't know, and then, or that you know aren't right, and then you can get the right answer. All right, we're going to come back to the why of that today at the end, hopefully, or maybe tomorrow. You need to get your gold sheets out. Yesterday we spent some really good time going through all of this. And the bell rang in kind of a rude way. It kind of like interrupted a good conversation we were having. Friends, you can kind of see that there's a really nice pattern that happens here. We're going to look at that pattern in just a moment. But prior to that, I want you to use this bottom row. Hopefully you didn't start coloring in that bottom row. That bottom row is there for a reason, but I didn't want to write why yet because I didn't want you to, get distracted. So we're going to write that in right now. What's that? Oh, you guys need paper? I've got papers for you. So you can watch the wonderful video where we talked about the front. We're gonna fill this in. And if you want to discuss really loudly, you totally can. All right. Anybody else need a gold piece of paper? All right. So on this very, very last row down here, friends, we're gonna write down magnitude at the maximum. So you'll notice on our little chart that at least in one case for each of them, there is a maximum value, right? Sometimes you get more than one maximum. I would like for you to quantify the magnitude of that value at the maximum point. You don't have any values like numbers, so you're going to do it with respect to 3 physical constants. The first one is the amplitude. The second one is the spring constant. And the third one is the mass of the block. So all of your answers here, all of the things that fill in these boxes, are going to have only these three variables, and then any other mathematical things like squares, square roots, halves, and things like this. Okay? I will do the first one for you. Oh, you already got that one? Oh, what'd you say, Hannah? It's A, right? The maximum displacement indeed is going to be A. Okay? Now, I'm going to give you a little piece of advice. When I do this, I never ever go in order because this is the hardest one. So don't do velocity next. Move over here and do the physics you know. Reason it through with physics. I'm going to give you a couple minutes to work by yourselves at your tables to talk it through. Fill these in. Velocity will probably be the last one you do. Okay? Go ahead and get started. Give it a shot. Talk to each other. Use your physics. You guys have got this. I know you can do it.
So the M's cancel.
Let's do this, shall we? All right, we did one. I need help with more. I don't want to just move across the page because I told you velocity was the hardest one. So tell me which one you're going to do next.
FS.
FS, she says. They say in tandem. Talk to me about it. How do we do it?
FS is negative KX, and you already know X is A, so it's going to be negative KA.
Oh, Fs is equal to negative Kx, X is equal to A. So the maximum Fs is going to be negative Ka. Bam. All right, one down, 4 to go. Who's got the next one? You can pick whichever one you want.
Got this. We believe in you.
Don't choose velocity. You're not ready to do velocity yet. Go for it.
Acceleration.
Do acceleration. What you got?
Negative K over M.
Negative Ka over M. Where did that come from?
The everything was AKM. We already knew what the force was. Acceleration is equals force over mass.
Okay, big A. I see what you're saying. Okay, say that one more time. I was getting super confused about acceleration. Say it one more time, the reason for this.
Acceleration formula is acceleration formula is force over mass. We already have a force, so we just need, and we are maximum of the variables.
Clever. Negative Ka over M. Love it. All right, 3 more to go. Who's got it? Sharing the fun, sharing the physics. What you got?
Oh, okay, I guess.
Thanks.
Spring potential, the equation for that is 1/2 kx squared. And since we know that x is a, it is 1/2 ka squared.
Love it. All right, 2 more.
That's fine. I guess it's fine, Spencer.
Go, Spencer.
For kinetic energy,
Uh-huh.
it's also 1/2 Ka squared because of conservation of energy.
Yeah. Nice job.
Yeah.
Conservation of energy says
You're right.
that
You owe me a fine.
if this has to be the biggest, where? It's the biggest over here, right? In E. At D, there's no spring potential energy. And if we've got the same amount of energy here as we have here, then it better be 1/2 Ka squared. All right, we're almost there. We have one left. Now we get the big one. I know some of you guys were just waiting because you wanted to do the big one, the big splash. Help me out.
Jacob, you got this. No, you're right.
You're not wrong. I don't even know what you have, but give it a shot.
The square root of
Well, why don't you walk me through it so that we can check it?
it. So because the spring potential max is equal to the kinetic energy max, you can do 1/2 Ka squared equals 1/2 mv squared, and then the 1/2s cancel.
I'm with you.
And then you move the m to the other side,
Okay.
and then you take the square root. And
We doing okay? Yeah. If you wanted to, you could also pull the A outside to take the square root, but you don't have to. Cool. Elizabeth thinks mine looks nicer. Yeah.
Okay, so it's not plus or minus.
Good question. Is it plus or minus? I was going to ask about these negative signs here. This is the magnitude at its maximum. So honestly, these can both be positive as well. I'm not going to get bent out of shape one way or the other. I just want you to know how to find the maximum. Okay? We've got 8 minutes, and in those 8 minutes, we're going to do some awesome stuff. Are you ready? Flip that paper over. So you may have noticed that as one thing gets bigger, another thing gets smaller. How did I get this? Oh, I put a mass on a spring and I watched it bounce. Watch, it's going to happen. It's going to happen right before your eyes. Whoosh. Right? It's pretty exciting. Bouncy, bouncy, bouncy. Slinky with a mass on it. Pretty great. Okay, so I took that video and then I threw that video into Logger Pro and I got this graph. It's the same as the one you have up there. It might not be the exact same one. I don't remember for sure, but it's the same idea. You see that as one thing goes up, this is the displacement. Another thing comes down. Okay, so this is the displacement. This is the velocity. So I went, I got all those points. And then I want to show you a couple of cool things about this. Question?
You said we missed that lamp for like 15.
Oh, maybe we do. Yes, we've got lots more minutes. Perfect. So many more minutes. I'm just going to keep talking until the bell rings, so I don't really care how many minutes it is. All right, here we go. I know, it's so cool, isn't it? There's my equilibrium. Take a look. When my displacement is at equilibrium, what do you notice about my velocity? Holy cow. And then the next time, it's at a minimum. And at the next time, it's at a maximum. Do you see how cool this is? And indeed, you can do the other half of it too, because you can see that when the displacement is at a maximum, what do you notice about the velocity? It's at 0, right? So when it's really, really far away, indeed, the block stops. And then it gets faster, and then it gets faster in the other direction. Are you with me? It's awesome, you guys. We have this nice sine curve and this nice cosine curve or whatever, because here's the secret. I have to tell you the secret. Sine and cosine are really the same thing. They're just shifted. That's it. Some of you are like, well, duh, I knew that. Some of you are like, wait, what? It's kind of weird. Let me tell you, because we're going to do some analysis with this, okay, that if you look up here, right on these things, right over here and right over here, you see an equation that's written out like this. Y or X or whatever is equal to A sine BT plus C plus D. And that might look scary to you. It might not, but it might. And if it does, I just want to tell you not to be scared, because this statement that I just wrote there in pink is to a sine curve exactly what y equals mx plus b is to a line. Okay? This is just the general form of a sine curve. That's all it is. Okay? C and D don't really matter, because really all they're doing is shifting it over and up and down. That's it. So those shifts don't really matter. The things that I care about the most in this statement, kind of like how I often get rid of B here, right? That's just shifting it up and down. Same, is the A sine B times T. And I want to tell you what those things mean, okay? In the displacement graph, well, actually, hold on, let me think about this. Yeah, we can do this. In the displacement graph, I'm going to call this delta X just to talk about it kind of like our pictures were before, okay? What's the biggest that sine can get? 1. What's the smallest sine can get?
-1.
-1, right? It goes from 1 to -1. If the sine BT is 1, that's the biggest that this value can be. Are you with me there? What is the biggest displacement that an object can have if it's in simple harmonic motion? A, it's the amplitude. That's exactly what that stands for. That A really is A. That is the amplitude of the function, okay, of the oscillation. Now, I told you that it can be sine or cosine, and it doesn't really matter. And if you look carefully up here, these are both listed as sine, because that's just the general form. Now, if we think about this, and we think about pulling that block and letting go, if we started at A, that means that we need our thing to start at 1 when time equals 0. Does sine start at 1 when time equals 0?
No.
It doesn't, but what does?
Cosine.
It does. So instead of writing sine, we're going to write cosine. So we're going to say that delta X is equal to A times the cosine of Well, it's got to be the cosine of something. And what is that something? It is b, but we need to know what that b is. I'm going to tell you what b is. It's close. It's not quite, it's like related to, but not quite the period. Cosine of omega t. Omega, oh, we need to meet this thing. This is a new letter. Can you find it? It's not a W. It is a curly looking W-like thing, but it is not a W. It is an omega. This is omega.
Wait, can you write it capitalized or?
No, it has to be the small one because the capital one represents something completely different. We'll get there at the end of the year, but we're not there yet. I know. Just wait until April and you will be super happy, okay? But we're not quite there yet. Little omega and little omega represents, it's related to the period, but it's not exactly. It is called the angular frequency. Okay? It's the angular frequency. Okay? How are we doing so far? Are we okay? Okay. And we'll talk about how that's related to frequency later. I'm not going to worry about it, but I'm just going to leave that right there. Okay. So one could figure out, using the numbers on the chart, exactly what all of these things mean, but I don't have time to do that today, so I'm not going to. I'm going to move on for just a moment here and start talking about velocity. And the velocity, well, we know what velocity is. We defined that on like the third day that we were together.
First derivative.
We're not going there yet. We'll do it in just, I promise you, because I know that you're waiting for it and it's going to happen, but just hold on a second. What is velocity? Literally, what is it?
Displacement over time.
Displacement over time. Change in position over time, right? Okay. But then Elizabeth is just like, I gotta do calculus. And today is the day. It's happening. Are you ready? How many calculus friends do I have in here? Fantastic. Today's your day, my friends. All right. So here's the deal. We're going to find the derivative, right? Velocity is the derivative of position. If you're not a calculus friend, we love you a lot. And you don't have to be able to do this. It's okay. It's just one wonderful opportunity to do it. So we're going to do it. So V is equal to, what do we have to do? We have to do a little chain rule of time? It's going to be fun.
That's how I do
All right.
that. Wait.
Derivative of cosine is?
Negative sign.
Negative sign. And the derivative of the inside of omega t is?
W prime T prime. I don't know.
Okay, this
Omega prime.
as a function of t, right? Derivative as a function of t. So omega t,
W.
it's not W.
Omega.
It's omega.
He said W, so I said W.
Stop with the W's. Are we okay? Again, if you're not a calculus friend, that's okay. We still love you a lot, but we're just doing a little calculus fun for the day. All right, let's do it again. A is equal to delta V over T. So my calculus friends say, oh, I want to do the derivative again. Okay, we'll do it again. All right, what's the derivative of sine? Cosine. Not negative cosine. It's not how it works.
What?
Don't fight, friends.
No, it is.
Let's do calculus and be happy. That negative comes from here. What's the derivative of the inside? Omega. So we got A omega squared. How are we doing?
Why is A standing too?
Because it's just a constant. So when you take the derivative of the outside, yeah.
But the derivative of a constant is 0.
Right, but it's not just, it's a function that has that constant in front of it. So like if you take the derivative of 2x, it's just 2,
But
right?
Isn't that
Yeah.
the same as having the negative by the sign? What? You're a little behind what we're talking about. Fine.
All right.
I was just
Are we doing okay? I promise.
Yeah, okay.
We can do the math later. Is that okay?
Yeah.
Yeah, I promise. It does work. What's that?
It's okay. I couldn't do like a
All right. So regardless of whether you just got a really big kick out of getting to take derivatives in physics today, or you're saying, what's a derivative? And that's 100% fine to be saying that. Now we're going to do physics that everybody can do. Here it comes. F sub S is equal to negative kx, isn't it? Is equal to ma. And we've really talked about this as just the displacement at any given time and find the acceleration at any given time. But friends, now we can find it at any time. Are you ready? Here we go. Here we go. We're going to take delta x and put it in. Oops, not for k. For x. That would be confusing if it was for k. Whoops. Try that again. And we're going to take acceleration and put it in for a. Are you ready? It's going to be a beautiful thing. Here we go. So negative k times a cosine omega t is equal to m times negative a omega squared cosine omega t. Why are we doing this? We're doing this to find a relationship between our constants and the frequency of our oscillation. Okay? I love this because we have this nice, wonderful, cute little equation right here, Hooke's law, and we make it into this big, disastrous mess.
Yay.
Yay! But are there a few things that can be canceled here? Find something that can be canceled. A can be canceled. You're right.
Cosine omega t.
Indeed. Anything else? Negatives. It's much prettier now. K equals m omega squared. And that, my friends, is beautiful. Okay? That's a beautiful thing. Why are you saying the letter W? There's no W's up here.
Omega.
Omega is up there.
He was asking.
Yes.
Why I asked why I hearing W.
Oh,
W.
I don't. Okay, you're on my side. I appreciate you. Thank you. Thanks, yo.
It's
All right.
W. It's Omega.
All right.
Resembles a W.
No, it resembles
All
Omega.
right. All right. We're going to put this all together because we've got just a few minutes, and even Chance will agree with me now, right? Just a few minutes left. Okay, here we go. So really quickly, we're going to use this to make some magic happen here. So delta x, I'm just going to make a little chart here, and v and a, and just looking over here at these big long scary equations, what is the biggest value that delta x can have? A, right? When cosine omega t goes away? So that's going to be the biggest thing you're going to have. It could be A. What's the biggest that V could be?
Omega A.
It looks like a W.
But it's not. That's why we're helping you. So what is it? It's true. Yep. And how about for acceleration? A omega squared, right? Are you excited? Do you see what's happening here?
Yeah, I see what's
Yeah?
happening, but also-
So the biggest is going to be A. What's omega? Hold on. What's omega? If we solve this thing right here for omega, omega equals the square root of K over M. And that's A times the square root of K over M. And this guy here is A times, well, that's what, K over M? And then you flip your paper over. And what just happened? Holy bananas, they are. Did you see that? It's exactly the same thing. Put a big box around this if you haven't done it already, because that's a big deal. And we're going to do one more thing.
I don't have room. Yeah.
Oh, you don't have any room. It's just like this much.
Okay.
This much. You can write small. Okay. And that is that I want to make sure that we know the relationship between omega and the thing that we actually know, and that's frequency. Okay? Omega is related to the frequency that we know and love because omega is equal to 2 pi times our frequency, the one that we know and love. Okay? We'll talk about why that's true in a few days.
Wait. So period's like the reciprocal, right?
Mm-hmm.
Okay.
Yeah.
Just checking.
So they're all related. Yeah.
Is F frequency? Is it gonna change?
Say again.
Is F gonna be frequency? Or
F is frequency. Yeah. Yeah. So angular frequency is equal to 2 pi. You've probably heard of 2 pi before, right? Times the frequency that we know and love. Okay? So now let's do this. We're almost there. Holy cow. I can't wait. 2 pi f is equal to the square root of k over m. We could say that f is equal to, well, that's 1 over 2 pi times the square root of k over m. What does period equal? 2 pi times the square root of.
Period. Remember period.
Are we okay?
Why is it M over K?
Hold on.
Because it's the reciprocal? Yeah?
600 seconds.
Mm-hmm. So the period for this thing to bounce back and forth is dependent on what, friends? It's dependent on what? 2 pi, we don't care about that. Dependent on the mass and dependent on the spring constant. And, bringing it all back, is it dependent on the amplitude? No. That's why the answer is D here. Okay? It just happened. Did you catch that?
Like, it's 2 pi over omega.
There's no
It's
egg
like
in this.
period.
T is equal to 2 pi times the square root of m over k. I know, do a multiple choice question. I mean, really, come on. Have an awesome day, you guys. Be well.
Wrapping my brain around. Period is 2 pi over omega, right? Okay, I'm just like wrapping my brain around.